While chemists engineer molecular solutions to everyday problems, physicists are making discoveries that question gravity isn't what you think it is. Physicists in 2025 have developed theories suggesting that gravity might not be a fundamental force at all, but rather an emergent property that arises from quantum information processes. This discovery challenges everything we thought we knew about how the universe works and threatens to overturn our understanding of space, time, and reality itself. Researchers at Aalto University have created a new quantum theory of gravity that describes gravitational effects in ways compatible with the standard model of particle physics. This breakthrough came from developing gauge theories that treat gravity as a field emerging from interactions between quantum particles and the information they carry. The key was finding a mathematical framework that could bridge quantum mechanics and general relativity, something physicists have been trying to achieve for decades. These new theories suggest that what we experience as gravitational attraction actually results from quantum information getting distributed and processed throughout space-time. When massive objects like stars and planets exist in space, they alter the quantum information structure of space-time itself, and gravity emerges as a consequence of these information processing effects rather than existing as a basic force like electromagnetism. The mathematics behind emergent gravity theories push the boundaries of theoretical physics. Scientists have developed gauge theories that use the same mathematical framework successfully applied to other fundamental forces. These theories treat gravity as something that emerges from quantum entanglement rather than as an inherent property of mass and energy. The approach opens new possibilities for understanding how the universe began and could help solve mysteries surrounding black holes and the Big Bang. Experimental evidence supporting these revolutionary theories comes from gravitational wave detectors like LIGO and Virgo, which have recorded signals from black hole mergers showing subtle deviations from Einstein's general relativity predictions. These deviations match the predictions of emergent gravity theories that treat gravitational waves as disturbances in quantum information structure rather than ripples in geometric spacetime. Laboratory experiments are producing data that supports the emergent gravity hypothesis. Scientists have created quantum systems where they can control information entanglement between particles and observe how this affects gravitational interactions on extremely small scales. These experiments show that when quantum information becomes more entangled, gravitational effects between particles change in ways that match emergent gravity predictions but contradict traditional gravitational theory. The connection between emergent gravity and dark matter research has produced compelling evidence for these new theories. Traditional physics requires dark matter to exist because visible matter alone can't account for gravitational effects observed in galaxies and galaxy clusters. But emergent gravity theory suggests that what we interpret as dark matter effects might actually result from quantum information processing at cosmic scales, with quantum entanglement across vast distances creating gravitational effects that mimic invisible matter. Dark energy observations also support emergent gravity theories in unexpected ways. The accelerating expansion of the universe requires dark energy according to traditional cosmology, but emergent gravity provides alternative explanations. If gravity emerges from quantum information processes, then universe expansion could be driven by changes in how quantum information gets distributed across cosmic scales. As the universe expands, quantum information density decreases, potentially altering emergent gravitational effects and causing the acceleration we observe. The fundamental structure of space-time becomes radically different under emergent gravity theories. Instead of space-time being a smooth geometric surface curved by mass and energy, these theories describe space-time as a quantum information processing system. The familiar three dimensions of space and one dimension of time emerge from how quantum information gets organized and processed at reality's most fundamental level. Space and time aren't basic universe features, but emergent properties arising from deeper quantum information processes. These discoveries could lead to breakthrough technologies that manipulate gravitational effects directly. If we can understand and control the quantum information process that give rise to gravity, we might develop gravity shields protecting spacecraft from gravitational forces, or gravity generators creating artificial gravitational fields for space habitats. The practical applications extend beyond space technology into energy generation, transportation systems using controlled gravity fields, and construction methods that make heavy objects effectively weightless. Medical applications of gravity manipulation could revolutionize treatment of health conditions. Controlled gravitational environments could help patients with bone density loss, muscle atrophy, and cardiovascular problems. Research into how gravity affects biological processes could lead to new treatments for aging and genetic disorders influenced by gravitational stress on cellular structures. Black hole research has provided additional evidence for emergent gravity theories through observations that traditional physics struggles to explain. The way black holes radiate energy and evaporate through Hawking radiation makes more sense when gravity is treated as an emergent property of quantum information. The information paradox that has puzzled physicists for decades might be resolved if black holes are understood as quantum information processing systems rather than geometric spacetime distortions. The Big Bang itself becomes a different kind of event under emergent gravity theories. Instead of being a singular moment when space and time began, the Big Bang might represent a phase transition in the quantum information processing system underlying reality. This perspective could explain why the universe appears fine-tuned for complex structures like galaxies, stars, and life, with quantum information processes naturally leading to the physical constants and laws we observe. Researchers at major universities are developing experimental approaches to test emergent gravity theories using quantum computers and advanced particle accelerators. These experiments aim to create controlled quantum information systems where gravitational effects can be measured and manipulated directly, potentially providing definitive evidence for whether gravity is truly emergent or remains fundamental. The implications of this research suggest that our understanding of physical reality operates through mechanisms far more mysterious and interconnected than we ever imagined, with the most familiar force in our daily experience potentially arising from information processes spanning the entire observable universe. While